Hey everyone, welcome to This Explainer. I'm really glad you're here today because we are going to bridge a super interesting gap, the one between theoretical binary math and actual practical hardware design. Have you ever stopped to wonder how the simple addition you do in your head actually gets physically wired into a microchip? Well, we're going to unpack exactly that today. And don't worry, we're doing it without getting bogged down by a ton of intense, unreadable syntax. We're going to look at how numbers are coded, how they're added together, and how hardware engineers use Verilog to organize all of this immense complexity into really neat, manageable digital boxes.
Here is our roadmap for today. We're going to cover binary coded decimal, mastering Verilog module hierarchy, designing arithmetic circuits, arithmetic assignment statements, and finally, catching overflows and carries. So let's just jump right in.
All right, kicking things off with Section 1, Binary Coded Decimal Explained. Let's see how numbers are fundamentally represented in our digital systems.
So, what exactly is binary coded decimal, or BCD for short? Well, it's a completely fundamental concept that elegantly maps the everyday, human-readable decimal numbers we're used to right into the binary language of logic gates. Instead of trying to convert a massive decimal number into one giant confusing binary string, BCD just handles it digit by digit. It simply assigns a specific 4-digit binary code to every single number from 0 through 9.
Take a look at how this translation actually happens. We're taking those familiar numbers and mapping everything from 0 up to 9 directly into neat 4-bit machine-readable packages. Like 0 is simply 0000, and 9 is 1001. If you want to write a much larger number, say 1895, you don't actually have to do any complex binary math. You just string the individual BCD codes together. 1, 8, 9, 5. It's incredibly straightforward and makes translating human inputs into digital hardware a whole lot easier.
Now this brings us to a really fascinating puzzle in hardware design. We know exactly how to represent these numbers, and we know logic gates can easily add bits together. But here's the million-dollar question: why is subtraction so much harder to build into hardware? Like, why not just build a subtractor circuit and call it a day?
The truth is, hardware literally prefers to add. Building a completely separate, dedicated subtraction logic circuit just eats up precious space and resources on a chip. So engineers came up with a brilliant workaround called the 9s and 10s complement. Basically, they completely trick the circuit into performing subtraction by using simple addition. To subtract a number, first you find its 9s complement by subtracting it from a string of 9s. Then you just add 1 to get the 10s complement. Finally, you take that result, add it to your original number, and just drop the most significant bit, the carryover, and boom, you've just pulled off subtraction without ever using a minus sign in your hardware logic.
So now that we understand the math, how do we actually organize all the code? Let's move right into Section 2, Mastering Verilog Module Hierarchy, to see how this scales up.
Think of Verilog module hierarchy kinda like a set of nesting Russian dolls, or maybe a really organized box of Legos. As your hardware designs inevitably get larger and more complex, you can't just have all your logic floating around in one giant messy file. A top-level module acts as a hierarchical boundary, a neat organizational box that includes instances of smaller, highly dedicated lower-level hardware modules tucked away inside of it.
This diagram really nails the concept. See that thick black line acting as a boundary? That's our top-level module, and it's securely enclosing two specific submodules, an adder module and a display module. Notice how the outside world only ever interacts with the inputs X and Y, and the outputs going straight to the 7-segment display. All the underlying magic happens via those internal wires labeled W0 and W1, which connect the adder directly to the display. This modularity is a game changer. It means you can design a perfect adder, thoroughly test it, box it up, and literally reuse it anywhere without ever worrying about its internal wiring again.
So, we've got our hierarchical boxes neatly organized. Let's head into Section 3, Designing Arithmetic Circuits, and see how we actually wire up the logic inside them.
This is where things get really cool. Back in the day, engineers had to use structural representation. That means painstakingly typing out the code for every single AND, OR, and XOR gate, literally like building a house brick by tiny brick. But modern Verilog, it allows for behavioral representation. Instead of mapping out physical gates, you just describe the function naturally. You simply type assign S equals X bitwise XOR Y bitwise XOR sin. It represents the exact same physical circuit under the hood, but it's vastly easier to read, write, and debug.
Just to give you an idea of why that higher-level abstraction is an absolute lifesaver, look at this 4-bit ripple carry circuit.
See how those individual full adders are daisy-chained together? The inputs come in at the top, the sum drops out the bottom, and that carry bit is passed down the line from right to left exactly like a bucket brigade putting out a fire. Now just imagine writing the structural gate-level code for every single one of those blocks. You'd be staring at hundreds of lines of deeply confusing code.
Manually coding all of those gate-level connections is tedious, it's messy, and it's practically begging for typos. Which brings us right into Section 4, Arithmetic Assignment Statements, the ultimate shortcut.
Verilog actually gives us the ultimate shortcut here. Instead of mapping out a maze of logic gates or even writing out the behavioral XOR logic for an entire n-bit ripple carry adder, you can use a simple arithmetic assignment statement. You literally just type S equals X plus Y. No, seriously, that's it. When you use vectors, meaning X and Y are declared as multi-bit numbers, the compiler looks at the statement, completely understands your intent, and automatically synthesizes that entire complex ripple carry logic circuit for you. You just step back and let the software handle the underlying magic.
But of course, taking these higher-level shortcuts means we still have to keep an eye on the physical limits of our hardware. A 4-bit wire can only ever hold 4 bits. That takes us to our final stop, Section 5, Catching Overflows and Carries.
We really need to draw a stark line here because people mix these two up all the time. Carryout? That matters almost entirely for unsigned numbers. It's just what happens when your addition generates an extra bit at the very end. But overflow? That's a critical error state we absolutely must watch out for when dealing with signed numbers, like in 2's complement. Overflow means you added 2 positive numbers and accidentally got a negative number back because you exceeded the physical bit range. If you don't catch an overflow, your automated system might suddenly think it has negative fuel.
You can mathematically see an overflow happening right in the logic here. Check out what happens when we try to add +7 and +2. In 4-bit signed math, +9 is simply too big to fit, so it wraps completely around to a negative number. The hardware actually detects this failure by looking at the carryouts from the final 2 most significant bits, C3 and C4. If C3 and C4 have different values, if they don't match up, that is your system literally screaming that an arithmetic overflow has just occurred.
So how do we gracefully handle this in our Verilog code when we're using that awesome S equals X plus Y shortcut? Well, to catch those elusive extra carryout bits without breaking a sweat, we use a really neat trick called the concatenate operator. By using curly brackets, we can elegantly combine different vectors together side by side. If you concatenate a 1-bit 0 to your inputs, you expand their size, and you capture the final carryout bit in one smooth move. It beautifully simplifies our n-bit adder code while guaranteeing that no critical data is ever lost. We've covered some incredibly powerful concepts today, from the absolute genius of mapping decimal digits directly to BCD, to tricking hardware into subtracting by using addition, all the way to structuring beautiful modular Verilog code with built-in overflow protection. With all of these modular, abstracted building blocks ready to go, the real question is, what kind of complex, automated smart system are you going to design next? Whether you're building an autopilot module or a precise robotic arm controller, the logic is entirely in your hands. Thanks for hanging out with me for this explainer. I'll catch you next time.